We understand the charge on the capacitor. Now let's think about what we usually really want is the current flowing in the circuit. Well, we know that the current, we said before, the way we got into this mess, was that the current was dq dt. So let's just take the derivative, the time derivative of what we found as q. That was the charge, that was the EMF times the capacitance minus the EMF times the capacitance, e to the minus time over RC. Okay. So the time derivative of this is a constant, so that's just going to be 0. We really just have to deal with the time derivative of this part. This has time in it. So it is minus EMF times c. When you take the derivative of an exponential function, you keep it, but then you pull down the derivative of the part in the top. So that's multiplying this by minus 1 over RC, and then you keep the exponential e to the minus t over RC. So that cancels, the negatives become positive. Whew. And then you got I equals the EMF over R e to the minus t over RC. So now we have the current as a function of time in terms of the things we were given, the EMF of the battery, R and C. Let's plot it and see if it makes any sense physically. Time, current. At time equals 0, e to the 0 is 1. So it's going to start at t equals 0 up here at, if this is 1, EMF over R. That's where it's going to start. And if you know your exponential functions, this becomes big, this thing goes down exponentially, and it'll be exponential decay. Something kind of like that. So we have a big current at the beginning, and it goes to 0. And that actually matches physically what you'd expect, right? At first, when we close the circuit, when we first close the switch, there's no charge on this capacitor yet. There's no potential drop across this capacitor yet. All the initial potential drop goes across the resistor. So at the very beginning, the resistor doesn't even know that the capacitor is there. It's just like a wire at the very beginning because it has no potential drop across it. Therefore, you do, at the beginning, get Ohm's law. EMF equals IR. And that's why you get that initial current value. But as the current flows, charges up the capacitor, suddenly some of the potential drop from the battery goes at the capacitor, not the resistor. That's what we've been solving this whole time. So slowly the potential drops across the resistor goes down in time, therefore the current goes down in time. So physically, this answer makes sense as well. The main quantity you talk about from an RC circuit is the time constant. What is the typical time it takes for this circuit to go from when we threw the switch to when it reaches sort of a steady state? And it's usually not infinity. It really takes a long time for it to happen. It's usually sort of this 1 over e point. So we call that the time constant. And it's usually called tau, and it's equal to RC. It's a thing under the time in the exponential part. So it's called the RC time constant. Okay. So that's the behavior of charging a capacitor. Now let's look at the interesting case of discharging a capacitor.